Space technology. Space technology stands at the confluence of advanced engineering, innovative material science, and groundbreaking computer algorithms that together open up new frontiers in exploration, communication, and our understanding of the universe. Over the past several decades, what began as early rocketry and basic satellite work has evolved into a complex and multifaceted field encompassing everything from orbital transportation to deep space probes, sophisticated telescopes, and robotic explorers. Modern space technology has become indispensable not only for scientific research but also for practical applications here on Earth, such as weather forecasting, global communications, navigation, and climate monitoring. This discipline continually pushes the limits of human ingenuity, necessitating interdisciplinary collaboration that spans astrophysics, mechanical engineering, chemistry, and computer science. The evolution of space technology has been driven by the development of progressively more powerful and efficient launch vehicles. Early efforts in space exploration relied on relatively simple rockets using kerosene and liquid oxygen, but advances in propulsion systems have ushered in an era of reusable launch vehicles that combine economic efficiency with reliability. Modern rocket engines now incorporate innovative materials capable of withstanding extreme heat and pressure, while computer-controlled systems ensure precise trajectory corrections during launch and orbital insertion. These advances have not only reduced the cost of launching payloads into orbit, but have also paved the way for more ambitious projects, such as crewed missions to Mars and the establishment of sustainable extraterrestrial outposts. Advancements in material science have played a pivotal role in the progression of space technology. The development of lightweight composites, high-strength alloys, and radiation-resistant materials has enabled engineers to design spacecraft that are both robust and fuel-efficient. In the vacuum of space, where thermal extremes and micrometeoroids pose constant challenges, these materials provide the necessary durability while minimizing mass. Lower mass translates directly into reduced fuel requirements, enhancing mission flexibility and overall sustainability. Moreover, innovations such as 3D printing and in-situ resource utilization are beginning to revolutionize spacecraft manufacturing and maintenance, as materials can be produced or repaired on demand, even in remote environments far from Earth. In parallel with advances in propulsion and materials, control systems and avionics have seen transformative improvements. Modern spacecraft rely on highly integrated digital systems that coordinate navigation, communication, and operational tasks with unparalleled precision. Embedded sensors provide real-time data on spacecraft orientation, velocity, temperature, and structural integrity. This data is processed by sophisticated algorithms that not only execute pre-programmed maneuvers but also adapt, in real time, to unexpected variables such as space debris or fluctuations in the interplanetary environment. The combination of robust control systems and adaptive software enhances mission safety and efficiency, allowing spacecraft to autonomously adjust their itineraries during long-duration missions. Satellites have emerged as one of the most critical contributions of space technology to both science and everyday life. Initially designed for reconnaissance and communication purposes, satellite technology now underpins global navigation, weather prediction, and remote sensing applications. Modern satellite constellations are engineered to provide near-continuous coverage, enabling everything from high-speed internet delivery to detailed climate models. The miniaturization of electronic components has led to the development of CubeSats and nanosatellites, which, while small, can be deployed in large numbers to form coordinated networks across vast swaths of space. These constellations are revolutionizing data collection and transmission, as they can provide higher resolution images and more precise measurements than ever before, all while dramatically lowering the cost of deploying orbital systems. Deep space missions have expanded our knowledge of the far reaches of our solar system and beyond. Robotic spacecraft, equipped with an array of scientific instruments, have traveled to distant planets, asteroids, and comets, returning invaluable data about the formation and composition of celestial bodies. These missions have transformed our understanding of planetary geology, atmospheric dynamics, and the potential for extraterrestrial life. The technological challenges associated with deep space exploration are immense, transmitting data across millions of kilometers, protecting sensitive instruments from cosmic radiation, and ensuring onboard systems function flawlessly in harsh and varied environments require state-of-the-art engineering solutions. Advances in autonomous navigation, energy management, and thermal regulation are critical components that enable these spacecraft to operate successfully far from Earth's supportive environment. Observational astronomy has also been revolutionized by space technology. Space telescopes, free from the distorting effects of Earth's atmosphere, deliver unprecedented clarity and depth in astronomical imaging. Instruments such as the Hubble Space Telescope have provided breathtaking views of galaxies, nebulae, and distant star clusters, fundamentally altering our perceptions of the universe. Newer telescopes, now being designed and launched with even greater light-gathering power and more sensitive spectrometers, promise to reveal details about cosmic phenomena that have hitherto remained hidden. This leap in observational capacity is not only fueling scientific discovery but also inspiring a global fascination with the cosmos, as each new image deepens our collective understanding of how the universe operates. Space exploration is fostering international collaboration and spurring significant progress in scientific research and technological innovation. Agencies across the globe, both governmental and private, are pooling their resources and expertise to undertake projects that would be prohibitively expensive for any single entity. The increased cooperation has led to shared missions, joint research initiatives, and collaborative efforts in solving complex challenges such as space debris management and planetary defense. By leveraging diverse perspectives and capabilities, these collaborative projects drive the rapid evolution of technology and create a more unified approach to challenges that affect all of humanity. Moreover, these partnerships nurture an environment in which knowledge flows seamlessly between nations, further accelerating the pace of discovery and the development of new space technologies. Another emerging area within space technology concerns the management and mitigation of space debris. With the increasing number of satellites being launched, Earth's orbit is becoming progressively congested. This accumulation of spent rocket stages, defunct satellites, and other debris poses a risk to operational spacecraft and threatens the long-term viability of satellite networks. Engineers and scientists are addressing this issue by developing innovative tracking systems, collision avoidance protocols, and even active debris removal solutions. These efforts involve a combination of ground-based radar systems, onboard sensors, and internationally coordinated response strategies to minimize the risk of debris collisions in orbit. The drive to secure a safe operational space environment is pushing the boundaries of tracking technology and control algorithms, ensuring that humanity's activities in space remain sustainable and safe for future generations. Energy generation and storage represent critical technical challenges in space operations that researchers are meeting through creative engineering. Solar arrays, increasingly efficient and resilient, provide the primary power source for most spacecraft. These arrays convert sunlight into electricity through advancements in photovoltaic technology that have dramatically improved both energy output and longevity. Innovations in energy storage and power distribution allow spacecraft to operate during periods when they are not exposed to direct sunlight, ensuring continuous energy supply for critical systems. Furthermore, developments in nuclear power, such as radioisotope thermoelectric generators, RTGs, have proven indispensable for missions in the outer solar system where sunlight is insufficient. These power solutions enable spacecraft to maintain functionality over long-duration missions, opening up new possibilities for exploration far from our sun. The human dimension of space technology is being reimagined by a series of ambitious projects aimed at returning humans to the moon, sending astronauts to Mars, and eventually establishing permanent outposts beyond Earth. Such endeavors require comprehensive innovations in life support systems, habitat construction, and radiation protection. Engineers are developing closed-loop systems for recycling water, oxygen, and waste, ensuring that long-duration missions remain viable with minimal resupply from Earth. Advances in medical technology, combined with robust telemedicine capabilities, are also integral to supporting astronaut health in a hostile environment. The prospect of human settlement in space is coupled with a need to establish sustainable ecosystems, requiring innovative approaches to agriculture, waste management, and energy production. These challenges inspire a new wave of research that combines the rigor of science with the creativity of engineering, ultimately advancing our ability to live and work beyond our home planet. The economic implications of space technology extend well beyond the realm of scientific discovery and exploration. The development of commercial spaceflight, satellite-based internet services, and space tourism is creating entirely new markets and economic opportunities. This rapidly expanding sector is attracting investment from private enterprises and venture capital firms, which in turn fuels further technological advancements and the growth of ancillary industries. As space technology continues to evolve, its applications are becoming more diverse, supporting industries ranging from agriculture to logistics and from environmental monitoring to disaster response. The monetization of space-based services offers a route to sustainable economic growth and reinforces the idea that space technology is not solely the domain of national agencies, but a globally accessible resource that benefits all of humanity. In essence, Space technology represents one of the most dynamic and forward-thinking fields of human endeavor. By combining rigorous scientific inquiry, cutting-edge engineering practices, and visionary collaboration, the field continually redefines what is possible. The advancements in rocket propulsion, material science, avionics, satellite systems, and deep space exploration have not only expanded our understanding of the cosmos but also brought tangible benefits to life on Earth. The challenges of operating in the harsh environment of space stimulate innovation that reverberates throughout numerous sectors, ultimately resulting in technologies that improve communications, navigation, weather forecasting, and environmental monitoring back on Earth. Each breakthrough in space technology is a testament to humanity's insatiable curiosity and enduring commitment to exploring and mastering the unknown, pushing the boundaries of what can be achieved with imagination, collaboration, and technical prowess. As humankind embarks on increasingly ambitious projects, from establishing lunar bases to planning crewed missions to Mars, the role of space technology will undoubtedly grow in importance. The drive to explore new frontiers, to transform raw scientific ideas into practical applications, and to extend our reach both physically and intellectually makes space technology an ever-evolving frontier of human progress. The innovations emerging from this field are setting the stage for future generations to live, work, and thrive in environments that were once thought to be the exclusive domain of science fiction. Ultimately, space technology is not merely about traveling beyond our planet. It is about expanding our horizons, broadening our perspective, and building a future where the limits of exploration are defined only by our collective vision and determination.